Yes. Good evening, guys. So, what we were discussing in the last class? Yes, guys. So, what we were discussing? We have discussed the plane stress, plane strain conditions, and we have to start the deformations. Yes. Few materials we have to discuss. The few materials like we have to discuss about homogeneous isotropic material and orthotropic and anisotropic material we have to discuss. Note down. Isotropic material. What do you mean by the isotropic material? Anybody know? Note down isotropic material. Isotropic material. Anybody, anyone know about the isotropic material? And then we have homogeneous material. Homogeneous material. So when I just draw the point, so when you draw the uh, isotropic material, let's suppose we have the material and we got the 2 points, point A and point B. When the elastic properties are same in all the directions at a particular point, then what we say? That material to be called isotropic material. when the elastic property, let's say for a point, in this direction e1, in this direction e1, in this direction e1, x y z directions, let's say we have uh, the property, elastic property, let's say e1, but at point b we have the elastic property, let's say for example e2, e2 in all the directions. So what you're understanding from this point of view, isotropic material means you need to understand when material is free from what we call, when the elastic properties are same in all the directions at a given point, that particular material will be called isotropic material. Note down. When elastic properties are same in all the directions, that means it is independent of the directions, not independent of the points. When the elastic properties are same in all the directions at a point, then we say that material to be isotropic material. When elastic properties are different in all different directions at a point, that material will be called reverse of that, anisotropic material. Anisotropic material, that means if let's say we have the material at a point, elastic property at a point we have elastic property, let's say e1, here e2, here e3, here e4, e5, like that. But here for this material, here also e1, here also it is e1. Elastic properties are independent of the directions at a point, because at the different points you have some different elastic properties. E1 and e2 both are not same. That is the pure definition of isotropic material. But when we talk about the homogeneous material, let's say you have homogeneous material. For example, this is the material, and in this material I'm considering my 2 points, let's say point A and point B, something like this. And for example, if I just say elastic properties, now in this case elastic properties are not same. Elastic properties are not same in all the directions. Elastic properties are same at a particular specific directions, but for all the points it will be same. For example, if I show you by the diagram, at a point what you can draw corresponding to this homogeneous material. For example, here you can draw like this. Let's say at a point you have in this direction, x direction, you have elastic properties e2. It will be same for b also. For a, let's say it is e1, it will be same for b also. For here, let's say e3, it will be same for e3 also. That means when elastic so note down, when elastic properties are same in a given directions for all the points, then we say that material to be homogeneous material. Homogeneous material means independent of the points. Independent of points. Because at particular point, whatever x direction you choose, the material properties is e2. At b point e2. At c also, you will have e2 only. Here you will have e1. Here you will have e3. But homogeneous material is not a isotropic material, because at a particular point elastic properties are not same in all the directions. Elastic properties are different at a particular point in a different directions, but in a specified directions elastic properties are same in a given directions for all the points. Elastic properties are same in given directions for all the points. Right? No, all the examples like steel, copper, aluminum, whatever the engineering materials you have, you will have homogeneous and isotropic material combined. Means, suppose a material we have at A point, we have E, here we have E, here we have E. At B point, here also you have E, E, and E. That means in all the directions, elastic properties are same, but at a given specified direction also elastic properties are same. This material will be both homogeneous plus isotropic. We do not assume the any material which we use in a structure that is only follow isotropic or homogeneous. That never exists. They will exist together. But there is a third example I would say, that is orthotropic material. Orthotropic material means it is almost very similar to homogeneous material, right? But unlike in the homogeneous material, my friend, you will have multiple directions. For example, here you are choosing x y z direction, but if I select here e4 in these directions, here also we will have e4, here also we will have e4. In a specified direction, elastic property will same in at all the points, at A, B, and C. At all the points it will be same, it will be same, right? So but if I talk about orthotropic material, all of you have noted down the previous slide? Anyone yet to note down? Yes. Note down orthotropic material. Orthotropic material. Here in the orthotropic material, my dear friend, here we have to understand this type of material will exhibit different elastic property, different elastic property in perpendicular directions. Means at a particular point, I would say E2 we have, here we have E1, here we have E3. Means three mutually perpendicular directions planes are there. For example, they will exhibit different elastic property in a perpendicular directions. And if I talk about the example, then I have example as wood, graphite, uh, plywood, I would say. Again, it is wood only. Yeah, these are the examples, etc. Now, what is the difference between orthotropic material and homogeneous material? Anyone? Means I would say here we have the material. For example, A point and B point if I take, and if I select three mutually perpendicular directions, I will be having different elastic properties in a perpendicular directions. Now for B point, we might have possibility that here we might have E4, E5, E6. I'm not talking about these directions. Maybe they might be having the same E4 dash. Here it might be E4 dash. But I'm talking about perpendicular directions. Perpendicular directions will have different elastic property at different points. All of you are understanding what I'm saying? And in a broader sense, if I classify this anisotropic, which is non-isotropic, anisotropic, yes, any doubt? What's your name? Yeah. Anisotropic material, or I would say non-isotropic material. I have given one homo problem. All of you got the answer? Ellipse, major axis and minor axis. At one particular point, properties are different. Properties are different in different directions. That means at a point, for example, if I take a point, I would be having E1, E2, E3, E4, E5, E6. In all the different directions, you will have infinite directions, infinite elastic properties. But it doesn't mean that we have the infinite elastic properties. We have 81 total elastic properties. Now, some of you might argue, sir, why not infinite? That is again not included in mechanical, civil, or aerospace. That is a totally a different discussion. I need to go with the material science. Again, that is a useless topic. I cannot discuss. That will waste again 30 minutes. Now, one of the question is that, sir, you discussed for orthotropic material, you said 9 elastic properties will be there, or the elastic constant we may require. What are all those 9 elastic constants? So 9 elastic constants are, you can note down, Ex, Ey, Ez, mu xy, mu yz, mu zx. Then we have G, Gxy, Gyz, Gzx. But if the material is homogeneous and isotropic, like in our strength of material, Ex, Ey, Ez will be equal. You mu xy, mu yz, mu zx, Poisson ratio will be equal. Gxy, Gyz, Gzx will be equal. So if I just go back to the question, they ask one question like when you see one question, the number of independent elastic constant, the number of independent elastic constant for homogeneous isotropic linear material will be 2, right? Yes or no, guys? The total number of elastic constant will be what? The total elastic constant we may require is 4, right? Total elastic constant will be 4 for homogeneous isotropic material. But for independently point of view, we may require only 2. So yeah, for this 3D orthotropic material, the number of elastic constant will be what? Now here in the question, they have not properly mentioned the number of independent or dependent or total elastic constants. But in the option, when you see, they have not given anything regarding the total elastic constant. They have given the 9 as an option. That answer is correct, and they have given the answer based on the independent elastic constant. Total elastic constant, we may have 36, but out of that, only 9 will be required to specify it independently because we have symmetric matrix. We have symmetric matrix. When you write 9 by 9, again, that is not required. But if you are interested, I will send the documents. In that, because of symmetricity and because of moment equilibrium, you may require only 9 independent elastic constant. So if I ask you the 21 option, it is for what? Option A, anisotropic material. Option B, you need to answer me. Homogeneous plus uh, homogeneous plus anisotropic material. Option C, homogeneous plus orthotropic material. None of the above. Which option is correct? Which option is or are correct? See, my dear friend, when I talked about the anisotropic material, and I said that for anisotropic material, my dear friend, we may have to require, suppose at A point and B point, I have the material, and if I say anisotropic material, that means in different in a particular specific direction, elastic property has to be same for all the points. That is a condition for homogeneous material. But when you see anisotropic material also, anisotropic material will say what? Anisotropic material will say in a different directions you will have different elastic properties. So both are satisfying the criteria. So if I mention only homogeneous, that is also correct. And if I mention anisotropic material, if I mention only anisotropic material, that will be classified as homogeneous material plus anisotropic or non-homogeneous plus anisotropic. Tell me. Does all the anisotropic material need to be homogeneous material? Do all the anisotropic material need to be homogeneous material? Because I can have the example, suppose I can have the example here. Let's say we have E2, E1. If I need to specify it in this direction, it has to be same in at all the points. That means if I mention only anisotropic material, that does not mean that it is a homogeneous material. Check it out. If I mention only anisotropic material, so will it be satisfying the criteria of homogeneous or not? Yes. So both A and B will be correct. All of your understanding means we don't have any other option, my dear friend, where we can say anisotropic material can have non-homogeneity, right? Non-homogeneity based on the definition of anisotropic materials. But will that particular A option will always be correct? Please look at very carefully the question which I asked, because this type of question they can confuse you in examinations. Just read the statement of we have just now noted down the definition of what we call uh, isotropic material, right? Or whatever the definition we have noted down in different. If I select anisotropic material, like I told you, anisotropic material, here if I say at A point we have elastic property E1, at B point we have E2, at third dimensions we have E3. This is point A. Point B, my dear friend, if I have point B, if I have my dear friend, if I only say B point, then what will be happening? It might have these directions, let's say E5, it can have E6, it can have E7 also. So a homogeneous material, again, it is not giving you, sorry, the anisotropic material will not giving you the results of homogeneous. It is an anisotropic. That is, according to definition of anisotropic material is what? At a particular point, in a different directions, elastic properties are different. That's it, right? So for this is called anisotropic material, but it is non-homogeneous. Here you have anisotropic, but it is homogeneous. So for this type of material, you have 21. For this type of material, you have elastic constant more than 21. So this is not correct. Understanding all of you? It has to be homogeneous and anisotropic material. Understanding or not, all of you? Yes. And if I keep the option, let's say, if I keep the option for 18 question, like for orthotropic and homogeneous material, the number of independent elastic constant will be what? Then what will be the answer? Similarly, question number 18, I am keeping just like in a 3D. Let me remove this matrix. In a 3D orthotropic plus homogeneous material, the number of elastic constant will be what? What will be your answer? Number of independent. So first of all, we have to make one material where we have A point and B point, and then we have to assume that orthotropic material will have different elastic properties. For example, E1 we have, here we have E2, here we have E3, and here we have my different. I said orthotropic and homogeneous. That means here we might have, once again, homogeneous means in a specified direction, elastic property has to be same. Elastic property has to be same. So again, my different, this type of material is what? Orthotropic material also plus homogeneous. Understanding? So what will be the number of independent elastic constant? And once again, the answer will be 9. Make a note of it. Is it done, all of you? All of you have noted down? Done for all? Is it done? Yes. Note on the next topic, deformations. Deformations. This is a very important topic that we are going through right now. Deformations means, let's say we have the material. and we are deforming by applying the load P. If I apply the load P, uniaxial load, then the material will may stretch in this direction like this. The material may stretch in this. And one more thing, example of anisotropic material, note down. Cracked glass. And yeah, that is a one example. Whatever the glass is there, if it is cracked, then elastic property will become different in all the different directions. So yeah, the deformations, not on the deformations. Here we have the length L, for example. The length will become L dash. Now I need to find what is the deformations. What are the deformations? So we know that is strain in x direction. We know change in the length by original length. Whatever the change in the length will be, L dash minus L, that will be change in the length. Final length minus initial length divided by initial length. So from here deformation I can get epsilon x into L. Epsilon x into L. But this is valid. This is valid if epsilon is constant throughout the length with respect to axial direction x. If epsilon, that is a strain in x direction, if it is same for this material, then only we can write like this. But whatever the strain, let's say strain they have mentioned is strain in x direction, it is varying with respect to x, something like this, e to the power minus x. Exponentially it is varying. That means here the deformation is less, here the deformation is more. For example, exponentially the variations are there. In that case, delta L will be determined by integration from 0 to L. I need to select the element over which the variations of epsilon x will be given, and then I need to integrate. If it is constant, if epsilon x is constant, I can take out of the integral and I can write dx 0 to L, and you know that that is L. That is a very important thing. This is valid if epsilon x is a variable. No doubt, very important. Is it done for all? Can I move to the next segment? No down. Hooke's law. So by Robert Hooke's law, we know that sigma is what? Strain into E. Strain in x direction, we know sigma by E from this. And we also know delta L by L. So what we can write delta L? Sigma into L divided by E. Sigma we know P divided by A, L divided by E. But this is valid if uniform is strength, if uniform is strain along the length. If epsilon x is constant, then only we can write like this. Otherwise, we cannot write. If epsilon x is variable, then what we can write? Epsilon x into E dx from 0 to L. Then delta L, we can further write sigma divided by E into dx. Then further we can write P into dx divided by A into E. We have to integrate it from 0 to L. 0 to L. If epsilon x is variable, then we have to integrate it. Once it is done, let me know. Done. Done for all. Is it done? Let me check whether there is any question based on this. There has to be question. Just wait. Just wait. Now, whatever the question you are seeing right now, you try to solve. What they have mentioned: a horizontal bar which is fixed at one end, a horizontal bar which is fixed at one end, and when it is fixed at one end, we have the length L. We are applying the load, axial load P, in this direction like this, where x is varying from x equal to 0 to x equal to L, right? And the length is varying as 1 meter, means the length is given as 1 meter. The cross sectional area they have given as 100 mm square. If elastic modulus is varying E of x, 100 e to the power minus x gigapascal, where x is length in meter along the axis of the bar, the axial load P is nothing but 10 Newton, that means 10 power 3 Newton. What is the axial displacement at the free end? So again, E of x is varying. See, in the formula, when you see P of dx, A into E. When P is varying, A is varying, E is varying. Anything is varying, we have to integrate. And I told you, even I told you this thing also, epsilon x into dx, sigma divided by E, capital E into dx. You can see from here, if E is varying, then strain will also vary. When strain will be varying, when the strain is variable, then I need to integrate. This question they have asked in GATE 2017 mechanical for 2 marks. Right. So now you have to perform the integrations, but you need to be very, very careful about the units. The unit they have asked in mm. So very first thing is that you try to write everything in meter. You write everything in meter. You integrate, you perform integrations, and you write in terms of meter. P is what? 10 power 3 dx. Let's say for example dx only. Area is they have given 100 mm square, so I'm converting into 10 power 6 meter square. And then we have Young's modulus, e to the power minus x, so 100 into e power minus x. Gigapascal, 1 gigapascal, we know that 10.9 Newton per meter square. So, and from 0 to 1 meter. Everything you try to convert in meter, then only you can substitute the limits in terms of meter. When you calculate delta, this question is simple, but very tricky in terms of unit, right? So when you calculate delta, you will get 1.718 into 10 power minus 3 meter. But if you write into 10 power 3 mm, you will be getting 1.718 mm. So what should be the answer? 1.718. No doubt. You cannot write E in terms of Newton per mm square. You cannot write this will be mm square, and after that you are keeping in 1 meter. No. Or it is better that you try to write everything in mm square, then you substitute 1 into 0 to 1000 mm like this. On the other way, you can get the answer directly straight away. But once again, you need to be very careful. Here, they have clearly mentioned that x, whatever the e to the power minus x, x is what in meter. That's why you cannot do that. Understanding my point? All of you understanding? We have to convert first in terms of meter. Yes or no, guys? Tell me. All of you understanding? Here, e to the power minus x gigapascal they have mentioned. So we have to write everything in terms of meter. Whatever the x limit is there, we have to keep in meter only. Not only that, unit in terms of meter, everything in terms of meter only. To make uniformity or to maintain the uniformity in the dimensions, right? Once it is done, let me know. Is it done for all? Can I move to the next segment? Note down bars in series and parallel. This topic we are discussing, and very first topic we are discussing is bars in series. Two bars are connected in series combinations. For example, example number 1, we have, for example, we have fixed end where one rod is connected. Then we are connecting other rods where we are applying the load P 10 kilonewton. A, B, C. Note down here you will be having EAB that is given as 200 gigapascal. EBC, that is given as 70 gigapascal. Diameter of AB will be given as, you can write 10 mm. Diameter of BC, you can write 30 mm. Find A. Deformation in the bar BC, the displacement of point C, the displacement of point B, maximum stress in member AB, B. Just wait, guys. Just wait because power is gone. Meanwhile, you can try that question. Meanwhile, within 2 minutes, I guess it's will come. Now, meanwhile, you can try that question for all the question. I mean, whatever the A, B, C, D, F, all the 5 questions you can try. A, B, C, D, E, yes. Length I have not given, right? Just wait. Yes. Just wait. I'm starting now. In few seconds. Yes, I'm audible now. So here you can just note down. Audible, right? Hello, hello, hello. Note down the length. Length I have not given. So here to here, the length is 200 mm. 500 mm. Now start trying this question. Solution. First of all, we have to make the free body diagram. Try understanding how I am making the free body diagram. Based on that only we have to use it. Free body diagram. How to make the free body diagram? So very first thing is that I'm making the free body diagram of AB section. In AB section, my dear friend, this is the free body diagram for BC. This type of load is acting what P, and you know that at any moment, my dear friend, and for this case, only one reaction force will be there, that is in this direction, because you know that summation of forces in x direction has to be zero. Summation of forces in x direction has to be zero. So 10 minus Ra has to be zero. So Ra must be 10 kilonewton, and whatever the direction we have assumed, that must be correct in this direction, because load is acting like this. So the reaction force would be opposite of that with the equal magnitude. But here the question coming about is free body diagram. How to make the free body diagram? That is very, very important. For BC section, we are applying the load P, that is 10. To maintain this body under equilibrium, we have to apply the load what? In this direction also 10. But at the joint, we don't have any load, so it has to be nullified. So here also 10, here also 10. So what you're understanding from this static equilibrium condition is that the load at AB and BC both will be plus 10. Why plus 10? Both the loads are going away from what? Away from the cross sections, not towards the cross section. So that has to be positive 10 kilonewton. Make a note of it. Once you know the load, it will help us to calculate the calculation number A, the deformation in BC. The deformation in BC, we know is strain in x direction has to be same for throughout the length, because there is no such a variation they have given. There is a fixed E. See, there is a fixed E, there is a fixed area, there is a fixed load. The strain cannot change. Sigma divided by E, that is P divided by A. P is same, A is same, E is same. There are no such a variations when we consider the specific lengthwise. There is no such a variations. So directly we can use the formula PBC, LBC, area BC, EBC. That means I am applying the formula PL divided by AE. Right? PBC is what? 10 into 1000 into length of BC. Length of BC would be what? 500. Area of BC would be what? Diameter they have given 30 mm. That means pi by 4, 30 whole square. EBC is what? 70. But everything is what? Newton mm. It has to be Newton mm. But we know that 1 gigapascal, that is 1000 Newton per mm square. We know that. So we can write 70 into 1000 Newton per mm square. Everything you try to convert in mm, the answer must be mm. So when you just calculate, what is the answer you're getting? Check it out. The deflection BC, we also call deflection C with respect to B, will be what? 0.101 mm. Check it out. Are you getting the same answer? Very quickly. Correct. Deformation in BC, we also write deflection of C. deflection of C, this much of deflection happened with respect to B, not with respect to A. When we write total displacement, the total displacement of C, that means I want to calculate C with respect to A, C with respect to fixed. The total deflections, total displacement, not with respect to B, with respect to A only, because it is a fixed section. Because AB will deform, BC will also deform, right? AB will deform, BC will also deform because it is joined together with the series combinations, and BC, because of its own the load which we applied, it will also deform. So that's the total deformations we call, right? Let me not confuse you by 3 deformations, only 2 deformation will be there, right? That is what we need to find. Make a note of it. All of your understanding? So there is only one end is being fixed, not the both the ends. Once it is done, let me know very quickly. Is it done? Now, by default, note down the B option, B particular uh, question. The displacement at C. That means they are asking deflection at C or displacement at C, C with respect to A. That is the total displacement, total. That can be easily written as C. That can be easily written by different something like this: A, B, C. Now understand very carefully. You try understanding what I'm writing. Deflection of C with respect to B plus B with respect to A. Can we write like this? Suppose we have 2 points B and C, and I need to find the deflection C with respect to B. Then what we write? We write deflection C, that is equal to deflection at B plus deflection C with respect to B. Just like a vector, just like a vector you represent, right? But here my different deflection C, that is with respect to A, that we write also write total deflection, that must be equal to. Now how to find deflection at B? Deflection at B can be easily written as with respect to A. Now we have 2 points A and B. Then how to write deflection at B point? Deflection at A plus deflection B with respect to A. Deflection at A is 0 because it is a fixed end. So we can write deflection at B, that is equal to deflection B with respect to A. And that is what I have written. That is what I have written. We know the answer for this question, that is 0.101 mm. The next big question we have to answer, deflection B with respect to A. That is deflection in the AB bar. That means we know PAB, we know LAB, area AB and EAB. PL divided by AE. 10 into 10 power 3. The length will be what? The length we can write 200 divided by pi by 4 into 10 square into E. Young's modulus. Young's modulus will be 200. 2000. So deflection B with respect to A or deflection A B, the deformation AB will be what? It will be coming as 0.127 approximately. So when you write total deflection, that is 0.127 plus 0.101. When you calculate, you will be getting 0.228 mm. That's the answer for B. But when you notice, we have already answered the C part also. Deflection at B point, total deflection or displacement, we can also write with respect to B, that is 0.127 mm. This one we already calculated. We already calculated this particular displacements. Now, when you look at the D option, maximum stress in AB bar, maximum displacement, maximum stress in AB member, that is a load in AB member, area of AB member. You calculate and tell me the answer. For for E, the last part, the maximum stress in BC member, that is a load in BC member, area of BC member. You can also note down the last question as maximum stress in the bar, in the whole bar. Calculate it very quickly. Correct, correct. D, no, that is not correct. You have not converted in. See how you are saying the unit. You must say the unit also. 10 into 1000 divided by pi by 4, 10 is square. So when you write, that must be in megapascal directly, because 1 megapascal is 1 Newton per mm square. So when you calculate, you will be getting 127.32 megapascal. Or Newton per mm square. Maximum stress in BC member. So 14.147 megapascal or Newton per mm square. And this is E part. F part, I ask, what are the maximum stress in the bar? So this is the maximum stress in AB and maximum stress in BC. That has to be 127.32 megapascal. Make a note of it very quickly. Done. All of you have noted down. Tell me, guys. Now, note on the next question. Let's suppose, for example, we have the bar like this, where we are same diameter, but here we have the different lengths. A point, and here we have B point, C, and D. And for example, I'm applying the load. Here we are applying 2P. Here we are applying 3P. 8P. Young's modulus for AB, for BC, for CD, that is equal, that is to E. Cross-sectional area for 1, 2, third material, same. Cross-sectional area you can assume, and you can see from the figure also, they are same. Find out A, maximum tensile load, and compressive load in the bar. B, the ratio of maximum and minimum axial stress. Displacement of point D. So very quickly we have to calculate the reaction force. Let's say, for example, I am assuming reaction force direction to be like this. I don't know which direction it is acting. It may act in this direction, but I am assuming in this direction. For example, summation of forces in x direction has to be 0. And for this, I can assume any sign convention. It need not to be any precise sign convention. I'm assuming this to be positive, for example. So minus RA minus 8P plus 3P plus 2P, that is equal to 0. RA will be, we are getting from here, that is equal to, we are getting it as minus 3P. Minus 3P means our assumed direction is what? Incorrect. We have to change the directions. Or we can also write RA equal to 3P like this. So we have to just reverse our directions, something like this. We have to change our direction to be like this, 3P. That is the reaction force. Once we get the reaction force, we can draw the free body diagram for all the segments to get the forces for AB, for BC, for CD, my different. Now you just try to draw the free body diagram. Here we are applying 3P, 3P, right? At BC, in BC member, my different, if I just take in a BC member, if I want to draw the free body diagram, what is the load which are acting in BC member? Anybody know? What is the load? If I ask you in AB member, you know that minus 3P. But if I ask you what is the load in BC member, what you will say? See, to determine the load in BC member, my different, no, understand. That is, yeah, that is correct. But some of you still, you might have doubt. So for clearing that doubt, I'm just saying that for BC member, you try to assume either left side or right side. Anything you can assume. Do not consider both the sides at a time. Either left side you can assume or right side. But both the sides you cannot take at a time. Now, when you look at from left hand side, then what are all the loads which are acting by different? When you look at from the left hand side, you look at very carefully and tell me the loads which are acting here to the left of that. See, 8P is acting like this, 3P is acting like this. So the net force which are acting is 5P like this. So I must apply the load 5P like this. To maintain the static equilibrium, here it should be 5P. Then load should be what? Plus 5P. And even you can see when you connect the when you connect the both the members at this and this, 8P loads which are there, which are acting at B point. You can see very clearly. CD, you can calculate either from left side or right side. It is very easy to calculate from the right hand side. In the right hand side, when you see only one load is acting, which is like this, 2P. Now, if you have doubt, you can cross check from the left hand side. Left hand side, the loads which are acting here, it is 3P like this, 3P like this, but 8P like this. So total is what? 2P is going in these directions. So if I apply the load in CD, if I write, it will be plus 2P. Make a note of it. So we have to make the free body diagram. That is the very first step. Once it is done, let me know. So from this particular segment, if I'll ask you, what is the maximum tensile load? What you will say in whole bar? What is the maximum tensile load? Maximum tensile means out of the positive 5p and 2p, whichever is the larger value must be there. That must be the answer. And whatever the maximum compressive load, only one compressive load is there, that is 3p, right? 3p, like this. We don't find any other member which is being subjected to compressive load. So this is the maximum tensile, this is the maximum compressive. Now when the area is same, what is the ratio of the maximum and minimum axial stress? What you will say? What should be the ratio? First complete this one. Now my dear friend, you understand the very next segment which I am writing. See, the very next is the ratio of maximum and minimum stress. So P maximum, P minimum, because area is same. Load divided by area, area is same. What is the P maximum load which are acting? When you see from here, the maximum load is what? 5P. The minimum load is what? 2P. So 2.5, that must be the ratio. Now the next question, they are asking deflection at D, deflection or displacement at D point. That can be written as D with respect to A. That can be written as D with respect to C, C with respect to B, B with respect to A. Indirectly, we have to find CD deformations, BC deformation, and AB deformations. For that, PCD, LCD, area CD, ECD plus PCB, LCB, area CB, ECB, PAB, LAB, area AB, EAB. Put all those values and tell me the answer. Here PCD is what? 2P, length is L, area is E. PCB is what? 5P, L divided by AE. PAB is what? Minus 3P, because compressive. And according to our sign convention, whenever the load is coming towards the cross section, that must be negative. When you calculate, you will be getting 7 minus 3, 4 PL divided by AE. It is coming out to be positive. That means it has to be deformed in positive x directions, like this. Note down. If it is coming out to be negative, it has to be displaced in the negative x directions. That is the standard sign conventions. That's a very, very standard sign conventions, which we know. Once it is done, let me know. Done? All of it done? Example number 3, you just note down. Hello, hello, is it done? Note down statically indeterminate problem. Statically indeterminate problem. The statically indeterminate problem is basically when the number of unknowns are more than number of static equilibrium equations. Static equilibrium equations. Then we cannot able to decide the unknown only on the basis of number of static equilibrium equations. That means here if I talk about a beam, a bar, which is being, now there is a difference between bar and beam. Generally bar is of smaller diameter, beam is of what? More diameter or dimensions. Let's say both the ends are not fixed. Now both the ends are fixed, here A, here B, here C. Initially I was having only one end which is being fixed, other end are free to deform, but here no. So here let's say this is a steel, here we have or we can say aluminum. Yeah. So only with the help of equations, if I apply the load P here, so how many equations will be there? Correct, very good. Yeah, how many equations will be there? See, Ra and Rc. Let's say Ra and Rc are the number of equations unknowns which we have, right? And how to determine summation of forces in x direction, that is equal to 0. Static equilibrium equations. Ra plus Rc, that is equal to P. Only one equation we have, that is the first equation, but how many unknowns are there? 2. Only with the help of this fundamental static equilibrium equations, we cannot apply the logic of getting the answer from the static equilibrium, Ra and Rc. Something we have to do. What we can do? We can use compatibility equations. Compatibility equations. What is the meaning of compatibility equations? The total net deflection at point C, the total deflection at point C has to be 0. That means deflection at C with respect to B, B with respect to A has to be 0. Has to be 0. Right? So my different here you can write the length, you can take L, and here you can take the length as once again L. Young's modulus for steel is E. For aluminum you can write, we can write approximately E by 2, for example. Area you can consider, let's say the area is what? Here we have the area, cross sectional area A, and here you can write cross sectional area as 2A, for example. Now we have to find Ra and Rc. Deflection at CB plus deflection in AB has to be 0. Combined has to be 0, not individual necessarily to be 0. Now deflection in BC will be what? PBC. What is a PBC? What is the load in PBC? What is the load in BC member? Draw the free body diagram. What is the load in BC member? Tell me, guys. What is the load in BC member? Tell me, guys. Either you see from the right hand side or from the left hand side. In both the way, it has to satisfy the. You should be getting the same answer. But here, when you combine from the right hand side, you are getting what? Minus RC. Or when you see from the left hand side, what it is acting? What it is acting, my dear friend? Tell me. When the loads are going away from the cross section, that is plus RA minus P. Can we write like this? Because from here also, what you are getting, RC will be equal to P minus RA. So minus of RC will be RA minus P. That is a load which are acting in BC member. What is the load which are acting in AB member? From right hand side, from left hand side, RA and RA. Or from the right hand side, you can also write P minus RC. P minus RC. Right? So make a note of it. So PBC, we know that minus RC. PAB, we know that P minus RC. Now we are getting the only one unknowns, RC and RC. We know L, we know A, we know E. We can able to equate to 0 and we can get at least RC. Once we get RC, we put over here, we will be getting what? RA. And that's how we are getting the unknowns RA and RC with the help of static equations and compatibility equations. All of your understanding? Anyone having any doubt? No. Where the derivation is needed? No, not needed. That's a directly known thing, right? We can observe very clearly that the net deflections are 0. Now the next point is deflection in BC plus deflection in AB has to be 0. PBC, we know that PBC. What is the PBC? PBC just now I have written minus RC L divided by area 2A E by 2 plus P minus RC L divided by A into E. That is equal to 0. And now here we will have this will cancel out. So we can write RC, that is equal to P minus RC. RC will be P by 2. RA will also be P by 2. From equation number 1. Now tell me the directions. Whatever the direction we have assumed, that is correct because we are getting the positive answer. We will see the derivation part. Now the next thing will be elongation of note on the next topic, tapered bar under axial load. We have tapered bar like this, where the diameter is changing from length to a different at different length we have different diameters. Let's say here we have the diameter D1, here we have D2, this is A, this is B. from a small end, you let's say at a distance x, you are calculating diameter dxx, and we are applying the load P, for example. Now tell me, my dear friend, if I'll be asking you what will be the deflections of B point with respect to A point. So now you cannot directly write PL divided by A. You have to integrate, because here P is not varying, E is not varying, area is varying. But how? Let's see. Area at any cross section XX, we can write pi by 4 dxx square. But how the dxx is varying? D1 minus D2 is varying over the length L. But dxx minus D2 is varying over the length of x. So from here we can write dxx as d1 minus d2 into x by L plus d2. So dxx can be written as kx plus d2, where k is d1 minus d2 by L. Axial variations, correct. So here we can write a deflection formula, P into dx divided by area into E. 0 to L, 0 to L, P into dx divided by area, pi by 4 dxx square. Dxx square, that means kx plus d2 square into E. Now everyone know the how to perform the integrations. Again, mathematics will play important role over here. Note down, then we will do the derivations, integrations. Done. All of you done with this? Now, my dear friend, we have to perform the integration from 0 to L. From 0 to L, we can write here it as P dx into 4 divided by pi kx plus d2 whole square into E. So we can write here P is constant, so we can write 4P divided by pi E. If I perform the integration, I will be getting what? Dx divided by x to the power n, we can write x to the power minus n plus 1 divided by minus n plus 1. But once again, if x is containing some other term, we have to differentiate and we have to write in denominator. I must sure that you know how to perform the integrations. So here we can write kx plus d2 to the power minus 2 plus 1, that is minus 1 divided by minus 1, 1 divided by k. Why we are writing k? Because d by dx of kx plus d2 will be k, and that k we have to write in denominator, right? Denominator. So delta we can write here, we have to write from 0 to L. So when we can write here minus 4p divided by pi e k 1 upon d1 minus 1 upon d2. See, at x equal to 0, at x equal to 0, what you have? The diameter is what? D2. The diameter is what? D2. At x equal to 0, at x equal to L, you have diameter D equal to D1. Right? That's how we are putting the limits. Then delta we can write 4PL divided by pi E D1 D2. Why? Because k we know d1 minus d2 divided by L. So some term will cancel out, and finally this particular answer we are going to get. This is the deflection of tapered bar. And what is the deflection of prismatic bar? PL divided by pi d square into E. Pi by 4 d square, that means what? A prismatic bar means which have the same cross-sectional area throughout of its length. Throughout of its length. Right? Let's say both the deflections are equal. If both the deflections are equal, then what should be the equivalent diameter of the prismatic bar? Suppose these deflections, I'm saying, it is equal to deflection of a common common prismatic bar of diameter d equivalent, for example, d equivalent. Then what should be the d equivalent? Under root of d1 d2, right? If I write delta of tapered section, delta of prismatic bar 4pl of same length, everything is same. Then what should be the equivalent diameter? That must be the answer. Note down. Now, my dear friend, try to solve the question. Try to solve this question and tell me the answer very quickly. All of you, please try this. A tapered circular bar of diameter varying from 20 to 10 mm is connected to another uniform circular rod of a diameter 10 mm, as shown in the figure. Both the balls are made up of both the bars are made up of same material with the Young's modulus 200 gigapascal. When it is subjected to the load P, the deflection or displacement at a point A will be what? At a point A means what? Total. They are asking total. Total will be A with respect to, let's say this is B, this is C. A with respect to C. I can write A with respect to B first and B with respect to C first. A with respect to B, that is a prismatic bar, deflections. This is a tapered bar, deflections. Add this one, you will get total. 4PL divided by pi d2 square into E plus load will be same in both the bars. Here length is 1, length is 2. Pi d1 d2 into E. So when you put the values 4 into P 30 into pi into 1000 into length is what? 1.5 into 1000. You convert everything in Newton mm square, everything will cancel out, you will get in mm. You convert everything in mm and Newton. That's how I have done here. 1.5 meter into 1000, that will become mm. Pi d2 10 square into E. E is what? 2 into 10 power 5 Newton per mm square plus 4p 30 pi into 1000. L2 will be 2 into 1000, 2000 pi Diameter is what? 20 into 10 into E, 2 to 10 power 5. So when you combinedly calculate and add it, you will get, tell me the answer. 0.015. Check it out. All of you getting the same answer? This question they have asked in Gate XC, I think. Gate XC PYQ. Now, you try understanding the next question and you tell me the answer for this question very quickly. Or just wait. It's better that we solve some good level problem. No, Gere will be more than sufficient. Just wait, guys. Just wait. Let me add the good question actually. Added, but where it is gone. Gere must be sufficient. Gere exam, whatever the salt examples are there. Almost same. You have the same questions there also, here also, in Gere and Timosenko. Perfect. So here we can write. Now try to solve this question. Try to solve it and tell me the answer. I stepped rod. Yes, yes. Timosenko, Gere almost same. Of length 2 meter is fixed at both the ends. The area of cross section of AB for this area is given as 200, and for this they have given 100 mm square. The force F is applied such that the section is displaced, such that this section B, the displacement of B, they have given 0.1 mm in the direction like this. Young's modulus of the rod, they have given 200 gigapascal. The applied force they are asking. See, deflection at B they have given. So I can write deflection B with respect to A. That is a deflection at B. Or I can also write deflection B with respect to C. On other way, we can write. So here they have given 0.1. Deflection in AB member. For that, we need to calculate load in AB member. Length of AB member we know. Area of AB member we know. E of AB member we know. The very big question mark is coming over here is that what should be the load in AB member. The load in AB member will be what? If you draw the free body diagram, that must be RA. That must be RA. So when you calculate, you will be getting what? RA Length of AB will be 1000 mm. I'm converting 1 meter to 1000, right? Area will be what? 200. Young's modulus will be what? 200 into 1000. So when you calculate here RA value, you tell me what is the RA? You will be getting 4000 Newton. You are getting what? The answer is 4000 Newton. But here, whatever the answer you are getting, that is of what? The answer for RA. That is not the answer for what we call F value. For F value, we need to calculate the static equilibrium RA plus RC. That must be F. But we don't know RC, so we cannot calculate F. So for that, we need to use compatibility equations. Net deflection has to be 0. For both the bars, it has to be 0. Combined, it has to be 0. So here we know PAB, that is we know 4000, length we know 1000, area we know 200, E value we know, again that is being cancelled out, so I'm not writing over here. Deflection at BC, free body diagram of BC will be what? RC, here RC. So minus of RC, length is what? 1000, area is what? 100, E. That is equal to 0. E will cancel out. This will cancel out. So RC will be what? 2000 Newton. Once we get RA and RC, you can calculate this 4000 plus 2000, that is equal to F, 6000 Newton. This question they have asked in GATE 2022 in XC for 2 marks. Anybody have any doubt? You can ask me. This you can also write. Deflection of B with respect to C, because from any fixed end, I'm calculating from any fixed end. That is my V's, right? All of you done with this? Can I move to the next question? Can I move to the next? Hello, hello, hello. Tell me guys, very quickly. Can I move to the next question? Okay. So yeah, this question you can solve as a homework. Easy one, because only one end is fixed, right? Only one end is fixed, so you can easily calculate this particular question. This question also you can try as a homework. This question you try now. This particular question you please try now. Same everything is same, but little bit of changes is there here. What they have mentioned, to maintain the, see here when you apply the load, here it will be A point, B point, C point, RA, RC. Steel aluminum, net deflection will be 0. E value for steel they have given 210. For aluminum they have given 70 gigapascal. To maintain the tensile axial strain of magnitude in steel bar, see, when I try to apply the load P, steel will deform like this. Simultaneously, aluminum bar will compress. So that's why in the steel we have the tensile strain, in aluminum we have the compressive strain, and that is very much clear from the free body diagram also. AB, that is RA and RA, that is a tensile. But for B and C, when you see, there is a compressive load of RC is acting. That's why the compressive strain is acting. Both are having same. See, whatever the deformation is there in the steel bar, elongation, the same compression will happen in the aluminum bar. Sorry. Here, when you just note down the next segment, the magnitude of the force P they are asking. Once again, it's a very easy question. No need to get panic. Here, tensile axial strain in the steel bar they have mentioned. What we know? Sigma divided by E. Sigma S in the steel bar. Steel bar is what? AB member. AB member means what? PAB divided by area AB into EAB. What is the load in the AB member? We know that, you know that. That is our RA. Area of AB is what? Let's say 1 meter square they have given. So we can write directly 1. 1. Young's modulus, they have given 210 into 1000. That's how they have given my different 10 power minus 6 mm per mm. So from here, what we can calculate RA value, we can get RA value as 210 kilonewton. Once we get the RA value, we have to calculate RC value. But how to calculate RC value? That's again a very simple one. Deflection in BC member, sorry, strain in BC member we know. What we know? Strain in BC member we know. So what is the strain we know? We know that 10 to the power minus 6. But they have given compressive minus something like this. That is equal to sigma of BC divided by E of BC minus 10 power minus 6. Sigma BC will be what? PBC divided by area BC into EBC. Once again, what we can write? Minus 10 power minus 6, that is equal to what? PBC. What is the load PBC? See that, minus of RC, minus of RC divided by EBC. Area BC is 170 into 1000. So when you calculate, you will be getting RA value as 70 kilonewton. When you know 70, when you know 210, when you club together, because you know summation of forces in x direction has to be 0. So from here, RA minus RC plus P, that is equal to 0. So P will be equal to what? RA plus RC, that is equal to what? 210. kilonewton. That must be the answer. Understanding all of you? All of your understanding? Tell me guys. Now, note down the next segment we call bars in parallel combination or composite bar. We call what we call composite bar. Before discussing the composite bar, I will be discussing one more last important problem. Here it's a very important. Now, all of you done with this? Can I move to the next question? Done. The rod AC is a rigid massless rod. It's a rigid massless rod. That means deflection in AC member will be zero. That is the first thing we must understand. Note down the E value for wire. Wire will be CD. E of CD, E of wire. Made up of steel. Length you can write here. Length of AB. Length of BC. Length of wire. Area of wire. Calculate or find A. Stress in the wire. B. Vertical displacement of the point C. Vertical displacement of C. So a wire is being connected with the rod. First thing we must understand, it's a pin connection. Means about this whole rod ABC will rotate like this. It can rotate by angle theta. Means whatever the deflection you are able to find here, if you are able to find the deflection at C, see whatever the deflection by which the rod is being deflected, the same amount the wire will be stretched out. That means if I draw the free body diagram, you will understand. But before that, I must say the blue color line will show there is no deformation is happening in AC rod. If suppose deformation is given, if suppose it's not a rigid massless rod, then what will be the condition? They might have given fixed condition like this. It might have deflected like this. If it's a rigid, it's a deformable rod, then they might have changed the loading condition, change the support condition also, because it has to rotate. But about the fixed point, it cannot rotate right now. It has to deflect like this. It has to deflect like this. So now if you draw the free body diagram, of rod A, B, C, very clearly when you can see from here, at B point 60 kilonewton load is there. Now when it is deflecting in the downward directions because of the load 60 kilonewton, the rod is going in the downward directions. What about the wire? The wire will be stretched out like this. It will be pulled by load P. Let me call this load to be PC. What about on the rod? On the rod, it will be acting like this. So combined together, what should be the free body diagram? The free body diagram should look something like this. Equal and opposite forces must be exit, right? In the wire, there has to be certain tensile load. That's why it is stretching in the downward directions, and because of that, the rod is deflecting in the downward direction at the point C, right? But what should be the load? The load must be in the upward direction for the rod A, B, C, not for the wire. Once we know this thing, we can just calculate summation of moment about A point equal to 0. We know static equilibrium conditions. If not, if you don't know, please go through engineering mechanics notes once again. So when you calculate B, that is 60 into this distance is what, 200 mm. They have mentioned it's 100 mm. 60 into 200 PC into 100. So when you calculate, you will be getting 120 kilonewton. With that 120 kilonewton, my friend, the tensile force is acting in the wire, right? So my question is here, how to calculate sigma in the wire? Now it's a very easy task for us. P wire, we know it's a P wire, that 120 into 1000 divided by area we know 300. So when you calculate, you will be getting 133.33 megapascal tensile. But what about the vertical displacement? Vertical displacement means here whatever the displacement is there, with the same amount the wire will be stretched out. Whatever the wire deflection is there, wire will be getting see, this will be the condition after deformations. After deformations, this will be the condition. The wire will be stretched like this because of the tensile load. And whatever the deflection at C, that is equal to what? Deflection in the wire. Because rod, there is no deflections. So P of wire, L of wire, area of wire, E of wire. So when you calculate, you will be getting 400 into, sorry, the load is what? 120. Sorry, here it should be not 120. It should be correct. It should be 300. The total distance from here to here will be 300 mm. So it must be 40 kilonewton. So it should be 40. 40 into 1000. Length of wire is what? 150. Area is what? 300. Young's modulus for the wire will be what? 200 into 10 power 3. So when you calculate, you will be getting what? Answer is 0.1 mm. Note down this question as homework. Every data is same. For question number 2, each and every data is same, just like a question number 1. But E value for AC, note down. Here you can note down as just it 100 gigapascal. Then you try to find deflection at C. What you have to find? You have to find deflection at C. But for that, you need to wait till the deflection chapter, because right now you don't know deflection because of the load which are acting PC at the ends. Right? So it's better that I should not give this question at this point of time. So you can just avoid this. But same question I will discuss once I will discuss. Yes, correct. Very good. Same thing I will discuss when I will discuss the Castiglione's theorem. Yes, that is what in our next segment I will discuss the Castiglione's theorem. Yeah, that is what strain energy method. Same thing. But in that strain energy method, again I will discuss once again very clearly. But for this, the problem which I have given here, question number 2. Now tell me, when you are about to find deflection at C point, you will differentiate dou u with respect to which load? The load PC or you will apply the virtual load? Perfect. Dummy load we have to apply. Very good. That is what I will discuss, right? All those things. Thank you all. Once it is done, you can leave for the day. Same question number one. You can also find by Castiglione's theorem if you know. Otherwise, I will discuss. You must be getting the same answer, 0.1 mm. Okay, yes, thank you. Okay.